Every day we are creating and communicating billions of terabytes of digital data. If it were written on paper, it would represent millions of libraries worth of data created every day. So we are always looking for ways to squeeze more data into less space. One approach is to design smaller and smaller memory media. But no matter the medium, there is a second mathematical tool we can use if we take advantage of the patterns in our data. We can use them to compress the size of our files as much as possible. The challenge is to do this compression in a way that enables us to reverse the process and uncompress the data without losing any information. This idea is known as lossless compression. Before the era of computing, we confronted this problem whenever we communicated over long distances, when we wanted to shorten our messages without losing any information. For this, people devised codebooks which map a specific set of common phrases into short letter sequences or codes using a lookup table. For example, the Siemens codebook contains common phrases used at sea, such as "I have one anchor on board," which can be expressed in code as AAC. While the Cotton Merchant codebook maps the phrase "our prices are below surrounding markets" to the word glass. So if two people share a copy of a codebook, they can communicate long phrases in just a word or two without losing any information. But there is a problem with this codebook approach, because these codebooks don't contain every possible sentence you might want to send, just the most common sentences for a specific kind of conversation. And if the type of conversation changed, the codebook would no longer be usable. This problem leads us to a more general approach where a single codebook is used no matter the type of conversation we are having. For example, one way we could do this would be to create a codebook based on the words of a given language. The idea is to map common words in any language to shorter sequences and to map the less common words to longer sequences. This approach is nice because all possible conversations in a language can be compressed using a single codebook. While this codebook works in general, no matter the conversation type, the compression achieved with this strategy is not as good as the codebooks designed for a specific kind of conversation. So we are left with a key problem. How can we achieve the high compression of conversation-specific codebooks while maintaining the simplicity of using a single general codebook which works on all possible conversations? A solution to this problem was presented in a paper published in 1978 by Jacob Ziv and Abraham Lempel, leading to what's known as Lempel-Ziv compression. The main idea behind this paper is that we should build a new codebook specific to every message we send. That is, we could take each message we want to send and scan it looking for repetition and design an ideal codebook for that message which maps the most common sequences in the message to short letter sequences. The sender can then use that codebook to compress the message. But of course, the receiver won't know how to interpret the data unless you first send the codebook as well. The goal would therefore be to design this codebook such that the codebook plus the compressed message is shorter than the original message. This is critical to make this method work. And then the sender can send the compressed message with the codebook attached. The receiver then uses that codebook to uncompress the message to get back the original. Because a dedicated codebook will compress a message so effectively, the compressed message plus the codebook will compress better than if we used a generalized codebook. But the extra insight Ziv and Lempel had was to construct the codebook on the fly, eliminating the need to send the codebook and decreasing the delay in codebook construction. The trick was to rethink how the codebook is constructed. Instead of scanning the whole message to determine an ideal codebook, which is then used to determine the compressed message as before, the codebook and the compressed message are built on the fly. So at first the codebook is empty, and as the message is scanned, the sender gradually builds up a codebook based on the letter sequences as they occur. The compressed message is also created at the same time using whatever is in the codebook at each step. So gradually building and applying a codebook on the fly allows the sender to send only the compressed message, because the receiver now has the ability to create the same codebook as the sender using the compressed message by simply performing the reverse operation as the sender. And that's the key insight. To see how this works, let's do a simple example. Let's say that Alice wants to send Bob the following message. Now remember, both sender and receiver start with empty codebooks. And the sender's encoder scans the message letter by letter, stopping anytime it encounters a letter or letter sequence it hasn't seen before. At first, it will always stop at the very first letter, in this case, A. And then it compresses that sequence using whatever is in the codebook at that moment, which is initially empty, so it sends the letter with the empty symbol attached to signal that it's the first time it's seen this letter. And since it's the first time the encoder has seen the letter A, it's added to the codebook as the first entry. The receiver does the same thing. The A arrives, and it knows it's the first instance of the letter A, so it adds it to its codebook in the same way. And the sender outputs A as the first letter in the uncoded message. Then the sender proceeds to the next letter, A, which it has seen before, so it grows this sequence by scanning ahead one letter to B to form the sequence AB. Since it's the first time the encoder has seen the letter sequence AB, it stops here. Instead of sending the sequence AB, it compresses it according to what they know is in the receiver's codebook up until that point. And this will always be the current sequence minus the last letter. In this case, this is A, which is in our codebook as A equals 1, thus sending AB as 1B. Finally, it adds this new sequence AB to the codebook as entry 2. On the receiving end, 1B arrives, and the decoder knows that 1 equals A, and so it outputs the uncoded sequence as AB, and then it adds AB equals 2 to its codebook in the same way as the sender. The sender proceeds to the next letter A, which it has seen before, so it scans ahead one letter to B, leading to the sequence AB, which it has seen before, so it scans ahead again to form the sequence ABB. Since it's the first time the encoder has seen the letter sequence ABB, it stops here. It compresses it according to what they know is in the receiver's codebook up until that point, for that sequence minus the last letter. In this case, AB equals 2. So it sends ABB as 2B. And it adds this new sequence ABB to the codebook as the third entry. On the receiving end, 2B arrives, and the decoder knows that 2 equals AB, and so it outputs the uncoded sequence as ABB. It then adds ABB equals 3 to its codebook in the same way as the sender. The sender proceeds to the next letter A, which it has seen before, so it scans ahead one letter to B, leading to AB, which it has seen before, so it scans ahead to form ABB, which again it has seen, and so it moves ahead to ABBA. Since it's the first time the encoder has seen the letter sequence ABBA, it stops here. It compresses it according to what they know is in the receiver's codebook up until that point. In this case, ABB equals 3. So it sends ABBA as simply 3A. Notice this time we compressed a 4-letter sequence down to 2. Finally, it adds this new sequence ABBA to the codebook as entry 4. On the receiving end, 3A arrives, and the decoder knows that 3 equals ABB, and it outputs the uncoded message as ABBA. It then adds ABBA equals 4 to its codebook in the same way as the sender. The sender proceeds to the next letter A, which it has seen, so it scans ahead to B, leading to AB, which it has seen, so it scans ahead one more. Since it's the first time the encoder has seen the sequence ABA, it stops here. Instead of sending ABA, it compresses it according to what they know is in the receiver's codebook up until that point. In this case, AB equals 2, so it sends ABA as 2A. And finally, it adds this new sequence ABA to the codebook as the 5th entry. On the receiving end, 2A arrives, and the decoder knows that 2 equals AB, and so it outputs the uncoded sequence as ABA. And that's how it works. Notice the sender is always adding what it hasn't seen to a growing codebook, and then sending that sequence minus the last letter in coded form using what they know is in the receiver's codebook. That's the trick. In this example, we're using a communication context, but even outside of communication, anytime we are storing data on hard drives, this method is used widely, from compressing DNA sequence to the popular zip compression protocol. It's also a key component of the GIF image format used when you compress images for rapid loading on the web. Aside from communication and storage, realize that this process is also learning about the data itself. It's scanning the data and building a model of the underlying statistical structure in real time. This led to applications in both pattern matching and machine learning. Without this algorithm and the ideas it inspired, you likely wouldn't be able to store as much data as you do or stream this video in the first place.